Are you aware of any ways to rewrite this expression?
I think we can rewrite it as a square root of a times the square root of b.
That would certainly be nice if we could do that, right? It feels natural. Unfortunately, we know in math things that feel good don't always work. But in this case, you're right. Yeah, square roots work well for multiplication. The root, all roots, not just square roots. The root of a product is the product of the roots. So that works. That works well. That is correct. By the way, do you think this would be true or false?
That's false.
This is false. This is a common mistake. Things that work for multiplication often don't work for addition.
Mm-hmm.
So, do you think this would be true or false?
False.
How could you figure that out? Well, subtraction is more like addition than it is like multiplication. So if something doesn't work for addition, it usually doesn't work for subtraction. Now, in this case, it would sure be nice if we could just do this. It would be nice if the root of a quotient was the quotient of a roots. So take a guess, does this look true or false?
True.
True. Why should we guess that? Well, we know that this kind of thing works for multiplication and it doesn't work for addition. Well, what is division more similar to? Division is more similar to multiplication than addition, so that can help us to remember the pattern here. So roots behave nicely for multiplication and division. They don't behave nicely for addition and subtraction. That's a little algebra that we'll be needing. Okay.
Okay.
So try this problem on your screen.
I feel stumped.
Okay, did you say you were stuck?
Mm-hmm.
Okay. Now, what you wrote down could work. You could have solved the problem with that approach, but it's probably not the simplest approach. So let's erase what you have on the right-hand side there. So what I was hoping here, so we don't know any direct way to solve this definite integral, or this indefinite integral. We don't know any direct way to find this antiderivative. So somehow we're going to have to rewrite it so it's something that we do know how to take the antiderivative of. I was hoping you would apply what we were just talking about a minute ago about square roots. How could we rewrite that expression inside of the indefinite integral?
Oh. Like that?
Okay, good. Have we taken the antiderivative yet?
Nope.
No, so we have to keep writing the integral sign. Okay, yeah, so that's what I was going for here. And we always have to put a dx on the end to show the end of the integral. Okay, do you see how to proceed now? That's possible. What would you do then? Let's see. I'm not quite sure how you came up with that 6 there. Oh, I see. All right. So it looks like you're trying to apply the power rule for antiderivatives, perhaps?
Mm-hmm.
Right. But okay, let's go to my screen and we'll talk about that.
Okay.
What's this?
Oh, it's 8x.
Plus c. That's right. That's just the constant rule for antiderivatives, right? That's our constant rule for antiderivatives. What's this?
3x plus c.
Good. What's this?
Don't we have to use chain rule here?
Now the key thing is 5 a constant or a variable?
Constant?
And is 8 a constant or a variable?
A constant?
So is 5 to the 8th power a constant or a variable?
A constant.
So we can just apply the constant rule.
Okay. So 5, 8, x. 5 to the 8th times x plus c.
Okay, so notice is this a power function? No, because power functions have to have a variable at the base. This is just a fancy way of writing a constant. What's this? I think I'll just show you what it is. Is 3 a constant or a variable?
Constant.
How about 2?
Constant.
How about 4?
Constant.
How about 2?
Constant.
How about root 2?
A constant.
How about 3 squared plus 4 minus root 2?
Constant.
So we just apply the constant rule. So how would you apply the constant rule here?
3 squared x plus 4x minus square root of 2x.
Okay, that's right. I think it's a little bit simpler to write it like this. But if you use the distributive rule, you'll get the answer that you mentioned. But I think that this is kind of what you would get to first here. So the point here is don't overthink constants. Does a constant have to be just one number? No. A constant can be a whole bunch of numbers. As long as you have nothing but numbers, it's a constant. As long as you have nothing but numbers, it's a constant. I think the thing that's confusing us here is square roots don't stop things from being a constant. Exponents don't stop things from being a constant. As long as there's no variables, as long as all we have is numbers, it's still going to be a constant. So what would this be?
Pi x cubed
Sounds like you might be overcomplicating it. So this is a constant, right? So it would just be that constant times x. Isn't that just our pattern for the constant rule? Here's the table that we worked on yesterday. Anytime you have a constant, the indefinite integral is just the constant times x. Anytime you have a constant, the indefinite integral is just that constant times x. It doesn't matter whether the constant has a whole bunch of numbers plugged into it. As long as it's a constant, you can still use that rule. So, for example, in this case, is pi a variable or a constant?
A constant.
How about 3?
A constant.
How about pi?
A constant.
How about sine of pi?
A constant.
Yes, because if you take the sine of it, if the number doesn't change, its sign can't change. You could test this on your calculator. It doesn't matter how many times you plug in sine pi in your calculator, you'd always get the same thing. A variable is something that can change. So how about pi cubed plus sine of pi? Is that a variable or a constant?
A constant.
So we just apply the constant rule like this. Okay.
So we're not taking like we're taking the antiderivative, right? So
True.
wouldn't the antiderivative of sine be something different?
The antiderivative of the sign of a variable is something different. The antiderivative of the sign of it. So what you're probably thinking of this rule here. That's a good question. I should have pointed that out. So you were probably thinking of this rule right here.
Mm.
Now, in this rule, what does x stand for? A variable or a constant?
Variable.
Well, that's the answer to your question. This rule only applies when you're taking the sign of a variable. That's something that's actually a good point. I should have pointed that out before, so I wasn't careful about that. I pointed out the things that were constants, but I also should have pointed out the things that are variables. So this rule only applies when you're taking the sign of a variable. This is how to take the antiderivative when you're taking the sign of a variable. It just doesn't apply when you're taking the sign of a constant. That shouldn't surprise us too much because I think we've seen a lot of rules in this class that are different for variables and for constants, right? I think we've seen a lot of situations where you have a different approach or a different rule when you're using a variable than when you're using a constant. So it shouldn't surprise us that this rule works for variables, but it doesn't work for constants. So I should have pointed that out. So for example, when does this rule apply? Does the base have to be a variable or a constant?
Variable.
Yeah. When does this rule apply? Does the exponent have to be a variable or a constant? The exponent.
Variable.
Right. All of these, how do you know? I didn't say that because we just take it for granted. What does x stand for in calculus?
Variable.
Right. So I should have pointed that out specifically, but that was kind of built into the table. When we use x, we mean this is a rule that works when this is a variable. That's why we specifically said this was a letter that was standing for a constant. For example, this is a good example here, the power rule. When does this power rule for antiderivatives apply? Should the base be a variable or a constant?
Power rule.
When does this power rule for antiderivatives apply? Should the base be a variable or a constant?
A variable.
And should the exponent be a variable or a constant?
Constant.
So it wouldn't apply to say this. This rule here has nothing to do with this. These are completely separate because this is not a variable. What is this? Well, we were just talking about that. Here we just use the constant rule. For this, you just use the constant rule because this is just a fancy constant. Okay. Let's see. Okay, yeah, so that's good that you asked that. That was something I should have pointed out before. After all, you could test this. You could test this by taking the derivative, right? What is the derivative of pi cubed plus sine pi times x plus c?
Well, that's the pi cubed plus sine pi.
Yeah, the key thing is you would not say that the derivative of sine pi is cosine pi. The derivative of sine pi is not cosine pi. That only applies when you're taking the sign of a variable, not a constant. Okay, so that would be an example of that. So what would this be?
The antiderivative of x to the fourth with respect to x. 1/5 x to the fifth plus c.
Okay, good. How would you do this?
Three-fourths x to the fourth plus c.
Good. Now, how exactly should you do this? Let's write this out a little bit more. I think the best way to do it is like this. First, we do this. Can you see how this is justified? This is what's called the constant multiple rule for integration. I think we've talked about this. We can take a constant outside of the integral. We take the constant outside of the integral. Notice there's a big difference between, so when the multiple is being multiplied times x, you just take it out of the integral. Since this is being multiplied by x, we just take it out of the integral. Does that make sense so far?
Yep.
And then this would be, well, what is the antiderivative of x cubed?
1/4 x to the fourth.
And now I think this is the answer you'd already mentioned. So anyway, I think maybe this would be the best way to do these problems for the time being, to specifically show that we're using the constant multiple rule. Or at least we should know in our head that that's what we're doing. We're taking the 3 out in order to work this out. Okay. So how would we work out this antiderivative? Well, I think in this case, I'm just going to show you how to do it. So what is this, a constant or a variable?
A constant.
So I can just take it out. That's the constant multiple rule. When you have a constant multiplied by a function, you can just bring the constant out of the integral. Now, these problems I think you already knew how to do. These you already knew how to do, but this one was giving us a lot of trouble today. This was giving us a lot of trouble today. Why? Well, it's just that most students don't realize that a constant can be, most people think that a constant has to be a single number all by itself. They don't think of this as a constant. But it is. The square root of 8 is a constant. You can check that. If you did the square root of 8 on your calculator, you could do it 1,000,000 times and you always get the same thing. It's a constant. So we can take this constant out just like we could any other. And then what? What would I do now? What should we write down here?
Square root of 8 times 1/3 x cubed plus c.
Now you can just apply the power rule to what's left inside. And you could stop with this, or you could multiply these together. And get this. Okay, so this is the new material that I wanted to go over with you right now, how to handle this type of situation. This was what was giving us trouble a few minutes ago, so we should pause and look at this to make sure we understand how we're doing this here. Do these steps make some sense now?
Mm-hmm.
Notice there's absolutely no need to do this. This is where you were going wrong before. Now, this is true. This is legal. You certainly could write the square root of 8 as 8 to the 1/2, but why should we? Why bother? The 8 is not the problem. This term is not a problem. It's just a constant. We have no trouble dealing with constants. We just use the constant multiple rules. That was the main thing that was messing you up previously. You were rewriting these as 8 to the 1/2 power. And that's true. That's perfectly legal. It's just not helpful. There's no need to rewrite this term because we can just take it completely out of the derivative. Okay. What's this?
The square root of 7x plus c.
Good. Now you have to be very careful here when you write this to show that x is not inside the square root. We have to show clearly that the x is not inside the square root here. Good. That's right. Now talk me through how you would figure out this antiderivative.
You rewrite it as x to the 1/2, and then you can use the power rule.
Okay, so tell me, what should I write down over here? Let's go through the exact steps. What exactly should I write here?
The antiderivative of x to the 1/2 with respect to x.
Excellent. So I wanted to check. We haven't taken the antiderivative yet, so we keep writing this that integral sign. That was good. Okay, so then what exactly would I write here?
2/3 x raised to the 3/2 plus c.
Okay, excellent. So what I want to do here is compare these two examples so that we can see how they're different. Notice in this case, the only way to take the antiderivative was to rewrite this as x to the 1/2 power. Whereas in this case, it was absolutely unnecessary to write this as 7 to the 1/2 power. It wouldn't be wrong to write it as 7 to the 1/2 power. If you wanted to, you could have written the answer like this. You could do this, but it's just completely unnecessary, an unnecessary complication. There's no need to write it as to the 1/2 power. So do you see the difference between these two cases? Here, we had to write this to the 1/2 power so we could apply the power rule. But we don't need to apply the power rule here. We can't apply the power rule. We can't apply the power rule to this because it's a constant. So the big difference here is that there's a totally different way of dealing with constants than variables. I think that's been a theme that we've seen in a bunch of the earlier sections. And that's what's coming up again here with antiderivatives. There's a huge difference between how you deal with constants and variables. The problem is a lot of students don't realize that this is a constant because it's more than just one number, but it is still just a constant. Okay, so far so good?
Mm-hmm.
Okay, any ideas about how you would solve this? What's the next thing I should write on the right-hand side of this equation?
The square root of 2 antiderivative of x to the 1/2
Good.
with respect to x.
That's good. Since we're having some trouble with this, though, I'm going to be taking even smaller steps, and I'll do it like this. So what you said was correct. What you said was correct. But maybe it's good to take even smaller steps and write it like this for the time being. First, we take the constant out. How do we know we can do this? This is the constant multiple rule. You can take a constant out of the antiderivative. And now you can write this as x to the 1/2. Well, wait, why didn't you write this as 2 to the 1/2? Well, you could if you wanted to, but what's the point? This has already escaped from the integral. This has already escaped from the integral. It doesn't need any more help. This is the thing that's having trouble getting out. So this is the one. It's almost like so the things inside the integral are trying to get out of the integral by kind of writhing. Like if you were in jail, you would try to like squeeze yourself through the bars, right? You would try to fold your body in a way that you could fit through. Well, the square root 2 has already gotten out of the jail. It doesn't need any more work. But this poor square root x, it's still inside the jail. It's the one that's going to have to contort and writhe and fold itself and change into a different form to try to squeeze some way between the bars here. Okay.
Mm-hmm.
All right. In any case, so now what? What should we write down now?
Square root of 2 times 3/2. 2/3 x raised to 3/2 plus c.
Okay.
And yep, I'll just leave it like that.
Yep, that's exactly right. That's exactly right. We could do another step. could do another step and write it like this, but I think we'd get full credit if we left it like this. Okay? The important thing here is that we treated the square root of 2 completely differently than we treated the square root of x, because one of them was a constant and the other one was a variable.
Is this just prep work for the next section?
Well, the next section is about taking antiderivatives, and that's what we're doing. So this is one of the types of, I guess the answer is no. The prep work, so I guess the answer is no, this is one of the types of problems in the section. One of the types of problems is how to take the antiderivative of this type of function. Okay, so let's try this problem on your screen.
I just leave it like this.
Okay, can you read to me aloud what your answer is?
The square root of 9 times x times 2/3 x raised to the 3/2 plus c.
Okay, I'm going to go back to my screen.
Guessing that's wrong.
Not quite. Yeah, there was a mistake there. So what's this?
5x plus c.
Now let me show you how to do this. We've been kind of doing this quickly without showing all the steps, but technically kind of what you would really do here is you would do this. Whoops, that's not right. The antiderivative of a sum is the sum of the antiderivatives. Antiderivative of a sum is the sum of the sum of the antiderivatives. So you can split it up like this. Antiderivatives work well for sum. And then what's the antiderivative of 5 dx?
5x plus c.
Good. And what's the antiderivative of x squared?
The 1/3 x cubed.
Plus d, say. When you do it like this, you only have to add one constant, because a constant plus a constant is just some other constant. So we only need to add one constant at the end here. Okay, so this would be the answer in this case. Now, the way we've been doing this in the past, we've been just going straight from here to here. We've been skipping this step, which maybe we shouldn't have been. I think that's where the confusion's coming in. We've been doing this in our head and just going straight to here. But maybe it might be safer to at least know in our head that this is what we're actually doing. Now, how would you do this antiderivative? Well, notice the big difference here is here we had a constant plus another function, but here we have a constant times another function. Well, that's a completely different beast. That's done completely differently. Here we use the constant multiple rule. So here's what we write down here. So here we used the sum rule for antiderivatives, and here we're using the constant multiple rule. Okay. Okay. Notice this is a 5, not a 5x. That's the most important thing. This is a 5, not a 5x. So, and then we'd end up here with this. And what is the, what do I write here? What's the antiderivative of x squared?
1/3 x cubed plus c.
All right, the key thing is notice, so this is 5 times 1/3 x cubed. It's not 5x times 1/3 x cubed. That was the mistake that we were just making on the previous problem on your screen. This is not 5x times 1/3 x cubed. Is just 5 times 1/3 x cubed. I can see how you get confused. It is confusing because here we did have a 5x. The rules are just different for addition than they are for multiplication here. So when you have a constant plus another variable, then you really do take the derivative of the 5 and the derivative of the x squared and you add them together. But when you have a constant times another variable, we don't take the antiderivative of this. We just pull it out of the antiderivative and multiply it by this antiderivative. And we actually saw a pretty similar rule for derivatives. We saw that it worked pretty similarly for derivatives as we're seeing here for antiderivatives. So to review, in this example, are we actually going to take the antiderivative of the 5?
No.
Actually, in this example, we did. Antiderivative of 5 is 5x. In this example, we did take the antiderivative of the 5 because this was a sum. But in this example, we don't take the antiderivative of the 5 because it's a constant multiple instead. When you have a constant times another variable, we apply the sum rule, and that means that we do have to take the antiderivative now of the 5. But when we have a constant times another variable, then we apply the constant multiple rule and we don't take its antiderivative. So let's look at this particular example here. In this example, did we take the antiderivative of the 5? Yeah, we do take the antiderivative of the 5 because it's added times the rest of the expression. How about in this example, did we take the antiderivative of the 5? No. Here we use the constant multiple rule, and we just take the constant out. So again, when you're having trouble, one of the best things to do is write down more steps, write down more little steps. We've been kind of skipping this step here, so we might not have seen that there was a difference between how constants are treated in sums and how constants are treated when they're a constant multiple. So when we're having trouble, it helps to write down each of those little steps. Okay, well, let's go back to your screen and look at what happened on that last problem. Let's see. Maybe we should just do the problem again from scratch. So you can erase what you have on the right-hand side there and try it again. So let's just erase what we have. Let's erase everything that's on the right-hand side and try it from scratch rather than trying to rethink our way through it. Okay, that's a good step.
Okay.
Okay, let's see. That looks good. So what should we have in front here? Root 9 or root 9x?
Root 9.
Yeah, just root 9. So what went wrong before is that we were putting in the root 9x. I can see how you could get confused about that, because if this was an addition, we would do it that way. So it's not easy. By the way, look at your second line. Your second line is root 9 integral of x to the 1/2. You can erase that dot. That dot doesn't really make much sense because we're not multiplying the integral sign times the x1/2. Okay, why don't we go back and redo that previous example on the same page, the root 3x. Just go ahead and erase your previous work and let's just do it correctly. This is one of the types of problems on the website, so we just want to make sure we know how to do that. So you can just erase all of your previous work for the root 3x, and we'll just do that again just to reinforce those ideas.
Okay.
Okay, that's right. So the key thing here is it's not root 3x in front. It's just root 3. And something else is, notice you rewrote the x as x to the 1/2 power. Did you need to rewrite the square root 3 as 3 to the 1/2 power? Well, no. You could have done that if you really felt like it, but there was no need to do that. Remember our little analogy. The only reason why the x is changing into a 1/2 power is it's trying to change its shape so it can squeeze out of the prison. But the root 3, it already got out, so there's no need to fiddle with the root 3 anymore. It's already free and clear, so we can just leave it the way it is with the root sign. Okay, I'm going to go back to my screen. All right, well, we had a little trouble with that, but I don't think that there's any particular reason to be concerned with that. There was just a bunch of things here we hadn't talked about yet for integrals. We had been skipping a couple steps here before. I hadn't really quite explained to you the sum rule and the constant multiple rule. I've been kind of trying to do this on the cheap. So this is something important to have in your notes here. These two examples I think are very important to have in your notes. This sum rule and this constant multiple rule. There's two different types of problems, and it's important not to get them confused with each other. A lot of the time when we're doing the antiderivative of a sum, we just go straight from here to here, and we don't write down this step. And I guess that's okay if you're confident, but you need to understand in your head that you really are doing this step. And that's different from using the constant multiple rule here. Okay, let's see. So let's write down this. Okay, so I'd like you to calculate this.
Sine of pi over 4.
And you can talk me through how you would attack that.
Use my calculator.
Okay.
Type in sine of pi over 4, and I get 0.707.
Okay.
And I guess I could divide by pi. Wait, no, that doesn't make any sense. Never mind. Yeah, I'll just leave it like that.
Yeah, good. So with the sine, who's the angle, the input or the output?
The input.
So which it tends to be in the form of pi, the input or the output?
The input.
As you can already see, right? We already saw the input had a pi in it. So there's absolutely no, the output is not going to be in terms of pi. I think you were probably thinking of the inverse trig functions. With the inverse trig functions, then the output tends to be in the form of pi. Okay, now here's the function maybe we haven't talked about for a while. Now, first of all, I'll just remind you that this has actually given us a lot of trouble in the past, because in the past we found it's very easy to confuse sine and secant, right? They both start with the letter S. So the sine is not the same thing as the secant. The secant is not the same thing as the sine. They're completely different things. Well, it's easy to say that, but it can be hard to remember it in the middle of a problem. But anyway, we just have to be careful to remember these are two different things. We don't want to confuse them. Do you know how to calculate this? How would you find this?
Right, I think secant is equivalent to 1 over cosine.
You think correctly. That's right. So talk me through how you would attack this.
I use my calculator and type in 1 divided by cosine of pi over 3. That gives me 2.
Okay, excellent. That's good. I probably might give you this little piece of advice, though. First, before you use your calculator, we've seen it's easy to make calculator mistakes. My advice is always, before you go to the calculator, write down on paper exactly what you're going to be typing into the calculator. We've seen how easy it is to make mistakes when we go to the calculator. So my advice is before you pull over the calculator, always write down on your paper exactly what you're going to then plug into the calculator. So, and then we did that. Not that you made any mistakes, you did it correctly. So that is the correct way to figure out that secant. Okay, all right, so you remembered that. That's good. That was something that we had to talk about. And again, we have to be careful not to confuse the sine and the secant. By the way, so notice, did you use this key on your calculator to find the secant?
No.
This is a totally different thing. This is a totally different thing. This is for finding the inverse cosine, right? That's a totally different thing. Okay. Okay. How could we? What's this?
Secant x, tangent x.
Great. Okay, we haven't talked about that for a while. That's good that you still remember that. That's good. That must have been imprinted there. Okay, yes. So that's one of the derivatives we haven't worked on for a while. That's good that you were remembering that. I don't think that's obvious. We just have to memorize it. Okay, how would you express this equation in words?
The derivative of secant x is secant x tangent x times tangent x.
Perfect. Excellent. Now, in this chapter, we've learned a new way to express this kind of sentence in words. So what's a different term that we can use to express this relationship in words?
The antiderivative of secant x tangent x is secant x.
Could you say that last part again? I zoned out.
The antiderivative of secant x tangent x is secant x.
Perfect. Excellent. Although probably we should say a antiderivative, because remember there's a bunch of antiderivatives. Good. Okay. Well, I don't know if this seems exciting or not, but this should be interesting to us because remember what we're trying to do here is learn how to find antiderivatives. Well, now it looks like we just added something else to our collection. Here's another thing that we can take the antiderivative of. Something else we can take the antiderivative of. Now we can add that to our list then. We now know how to do this. So what is this?
Secant x plus c.
That's right. How would you check that?
You can take the derivative of secant x plus c. You will get secant x plus tangent x.
Okay, that's right.
Times. Yeah.
Good. So remember that yesterday we were working on this table of indefinite integrals. Hopefully you have this table written down. So you can go back to that table and add this now to the list. Or if you lost, I should have said that that's something you should hold on to. So if you lost it, you can make another copy. I'll send you these notes after today.
Okay.
It's getting to be kind of a big list here now, right? So here we've added one more thing we can take the antiderivative of. This one seems a little bit different because it's a more complicated function. Most of the earlier functions were pretty simple things like sine, cosine, e to the x, x to the n. This is a more complicated function. But now we know how to take the antiderivative of that more complicated function here as well. Okay, good. So let's try this problem on your screen. And what we're just doing here is the theme of this chapter is that there's just a whole bunch of different problems testing how to do a whole bunch of new antiderivatives that we haven't talked about before. So we're just trying to run through all the various antiderivatives and integrals that are tested in this section to try to learn how to do as many of them as possible. So this is one of these.
Okay.
That is correct. Good. I'll go back to my screen. All right. I just wanted to point out that the reason this worked, you didn't write this step down, but I just want to point out this is a necessary step to think through in our head. First, we used the constant multiple rule to take the 8 outside of the antiderivative, and then we took the antiderivative. So I'm not saying you have to write this down. It's okay to skip this, but we need to know inside of our head that that's what we're doing, or otherwise we're going to get confused as the problems get harder. So you did this correctly, no mistakes, but we should just mentally recognize that we were actually doing something like this. Okay, good. And let's try this problem on your screen. This is supposed to be a 4, not a y.
Okay. Okay. Okay.
Perfect. Excellent. I'll go back to my screen. That's right. Okay, so you didn't make any mistakes. I just wanted to point out that we need to understand in our head that we're really doing this. What we're really doing is first separating this into 2 separate antiderivatives and then doing them separately using the sum rule. I'm not saying you have to write this down. If this is easy and clear for you, you don't need to write it down. If the problem was not easy and clear, it would be good to write down more steps. But as long as this was clear to you, it's perfectly okay to go straight from here to here. But mentally, we just need to recognize we're doing this. So notice the big difference between this and the previous problem. In this problem, you didn't actually take the antiderivative of the 8 because you were using the constant multiple rule. And the 8 escaped from the integral in the very first step. But in this step, you really did take the antiderivative of the 4. Because notice the 4 cannot get out of this definite integral until you take its antiderivative. The sum rule does not take the 4 out of the integral. It just puts it, it just takes it out of one big cell and puts it in a smaller cell. So we've separated the 2 prisoners into 2 separate cells, but the 4 is still inside the prison. You still have to take its antiderivative to get out. So this is what was confusing us earlier. And like I say, I don't think you should feel too worried about that. That was something I hadn't really explained very clearly before. We were getting confused about this before because I hadn't explained it, but now I think we're getting that right. Okay, all right, well, that's how you applied that antiderivative. I think we got that down. So that's another antiderivative to have in our pocket. Do you perchance remember this?
Secant x squared, well, secant squared x plus.
Which, as you remember, means the same thing as this.
Mm-hmm.
If you're going to do it on your calculator, it's probably better to write it like this. For purposes of the calculator, it's better to write it like this. But for purposes of your answer, it's probably better to write it like this, because this is kind of more standard, although you wouldn't lose credit for this. This is correct. Okay, well, you did remember that. That's excellent. Very good. Okay, so actually, now that I think about it, maybe we should do this. talk me through how you would do this problem.
Okay. So secant of x equals 1 over cosine of x. So secant squared of x is just, this would be 1 divided by the cosine of pi divided by 6. All that's, well, the bottom half of the fraction squared. This. I get 1.33.
That looks like a good candidate to change into a fraction.
Mm-hmm. So 4/3.
Okay, excellent. Okay, good. My one piece of advice again is, because it's easy to make calculator mistakes, I think that in this case, first I would rewrite it like this. It's always safest to write things down on paper exactly how you're going to type them into the calculator. Maybe you did this, and then go to the calculator. That way it's easier to check our work and avoid mistakes. By the way, notice this is exactly the same as this. Doesn't matter whether you square only the bottom or both the top and the bottom, because what's 1 squared?
1.
Yeah. So either of these would work. But this is maybe unnecessarily complicated. So I'll erase this. This is the simplest way to do it. Okay, it looks like you got that correct. Of course, we would never want to confuse this with sine squared. That's something to watch out for there. Okay, well, that was a little digression. Let's go back to this expression here. How would you express this equation in words?
The derivative of tangent of x equals secant squared x. Then you can say the antiderivative of secant squared x is tangent of x.
Good. Probably better to say a antiderivative, because there's many antiderivatives. But otherwise, that's excellent. Very good. Well, what do you know? It looks like we're ready to head back to that table, right? Now we have another entry that we can put in that table here. Why don't you study this sentence here then for a second?
Mm-hmm. Yep.
So what should I write now in the table? What's the next entry? Remember, this is our table of indefinite integrals.
You can write the antiderivative sign of secant squared x equals tangent of x plus c.
Right, we'll put in the dx, and then we have tangent x plus c. Okay, excellent. Okay, so all of these have to be memorized. I haven't tested them on you today, but previously you had all these other ones already pretty well memorized. The ones that are hardest to remember are these two. But when we went over them yesterday, I think we were pretty comfortable with them. Okay, so that's just another one in our series of antiderivatives that we need to know. Very good. Now, let me point something out here. This might seem like a big list, but there's many things that aren't in this list. Even though this seems like a big list, there's many things that are not in this list. For example, do we have a special formula for this? Well, maybe I won't put it right here. Do we have a special formula? Do we know how to do this?
Yeah.
Yeah. Remember what this is?
Negative cosine of x plus c.
Perfect. Do we know how to do this?
Mm-hmm.
Yeah.
That's sine of x plus c.
Good. So is this in the table?
I'm not sure.
This one here?
I can't recall if we if we have it in the table or not, but I mean,
Oh, well, I mean, is this one of the entries? So our table includes, so the table includes all of the antiderivatives we learned how to do so far. So is this in our table of all the antiderivatives that we learned how to do so far?
I believe so.
Yeah. Well, you know, because you wrote down the answer here. It was negative cosine x. And is this one of the ones that we've learned how to do so far?
Yeah.
Yeah. Is this one of the antiderivatives we learned to do so far?
Yeah.
Actually, I think the answer here is no. We have no idea how to do this antiderivative. You're probably thinking of derivative.
Right.
We know how to find the derivative of tangent x. But if you go back to the table, here's the only trig function lines we have. These are the only lines that we have here for trig functions. Sine, cosine, secant tangent, and secant squared. We have no idea how to find the antiderivative of a tangent. So far, so good?
Yeah.
Yeah. Why did you say we did? Well, you might have been confusing this with the derivative rules. We know how to take the derivative of any trig function. We know how to take the derivative of any trig function, but antiderivatives are harder. We don't know how to do this so far.
Is that something that we have to know how to do eventually?
Yes. Yeah. So we need to know what we don't know, and I'm not quite sure if this one will come up in your course yet. My only point I'm making so far is there's some things we know how to do and some not, and some of the ones that we don't know how to do yet, we'll have to learn how to do them. But first of all, we have to know what we can do so far and what we can't. So is this an antiderivative that we've learned how to do so far?
No.
That's right. Although that's a little tricky. Is this an antiderivative that we've learned how to do?
Yeah.
And is this an antiderivative that we've learned how to do?
Yeah.
Yeah. But there's still a bunch of things that we might not know how to do yet. So what are we going to do if we're given something we don't know how to do? Well, we'll have to use other tricks. Maybe we'll have to somehow re-express it so it looks like something we do know how to do. For example, how would you take this antiderivative? What would be your first step?
Rewrite the function as x to the 1/2. Well, the antiderivative of x to the 1/2.
That's right. Because this you do know how to take the antiderivative of. So the point is, if you're given an antiderivative that you don't know how to solve, try rewriting it as something you do know how to solve. And so that's something we might have to do with trig functions as well. If we're given a function of trig functions and we don't know how to solve it, we might have to rewrite it as something that we do know how to solve. Okay? Let's try this problem on your screen.
Okay.
Okay, good. Okay, excellent. So this is a very simple example of what I was just talking about. Does our table tell us how to find the antiderivative of 8 secant squared x? Well, no. 8 secant squared x is not in the table. But there was a very simple trick you could use. You could use the constant multiple rule to take the 8 out of the integral. And now what was left was secant squared x. Does our table tell us how to take the integral of secant squared x? Yes. So then you'd had success and you were able to apply the rules. That was a simple example of what I was talking about, but that was correct. I'll go back to my screen. Okay, so if you can read my writing here, this is a little harder case. Our table does not tell us directly how to find the antiderivative of 1 divided by cosine squared x. So we're going to have to try to think of some way to rewrite this as something we do know how to take the derivative of. We don't know how to take this antiderivative. We have to somehow rewrite this as something we do know how to take the antiderivative of. You can try this on your screen if you like. Any ideas about how we could rewrite this? What could we rewrite this as that we do know how to take the antiderivative of?
I know over cosine squared x. I'm not sure.
Okay, let's see. Can you think of any way to rewrite this expression? Any way to rewrite this expression?
Cosine x to the negative 1.
Yeah, although we probably wouldn't do that. Yeah, you'd have to write it like this. You wouldn't want to write it like this, because we know this doesn't mean exponent, it means inverse. Yeah, you could do that. That's right. Unfortunately, yeah, that would work. Let me give you a hint. Can you think of any way to rewrite this? What's a way to rewrite this expression?
1 over cosine of x.
Exactly. So what's a way to rewrite this expression?
Secant x.
That's right. These mean the same thing. That's a pretty important idea, so, whoops. Just to reinforce that, what's a way to rewrite this expression?
Secant x.
Excellent. Can you think of any way to rewrite this expression?
Secant squared x.
Like this?
Mm-hmm.
Okay, let's check that. So this really means this. And that really means this. And that really means this. And that really means this. Looks like we got it right. Okay, yes, it looks like that was right. So it's always best to take baby steps to confirm things, but it looks like 1 over cosine squared x really does mean secant squared x. So we'll just finish up with that problem, and then we'll be done for today. So to review and reinforce that, how can we rewrite this expression?
Secant squared x.
That's right. Because secant is 1 over cosine. So 1 over cosine is secant. So any ideas about how we might do this problem?
You can rewrite this as the antiderivative of secant squared x with respect to x, and then take the antiderivative of secant squared x, and that's tangent x plus c.
Okay, that's our answer then. Okay, all right, so that's what I meant when I said that this table does not cover all the possible cases. There's many types of problems that don't exactly match this table. So what do you do when you're facing a problem that doesn't exactly match the table? You have to find some way of rewriting the integral so it does match the table. This was a very simple case. Here we rewrote this using the constant multiple rule so that it would rematch, so that it would match the table. Or if you were given this, you would rewrite it like this so that it would match the table. This was a harder case. How can we rewrite this so it matches the table? Well, now we've learned we can rewrite that as secant squared x. Why is that helpful? Because we happen to know how to take this antiderivative. That's helpful because we happen to know how to take that particular antiderivative. Okay. All right. So it might seem like this is an unending stream of antiderivatives, but actually I think the table is done now. These are all the entries. These are all the entries in that table. That doesn't mean that you're done with antiderivatives. The next thing is to learn how to re-express things so they fit the table. The next thing would be to learn how to re-express things so they fit the table. But actually we're not so far off from that too. I've been kind of going over that with you as we went. So we've already gone over most of the re-expressions that you need. So most of the basic ideas from this section we've gone over. We haven't kind of quite put them all together yet into solving problems yet, but there's not much more new material in this section. These are all the basic antiderivatives. We have to learn now how to re-express things so they look like the table, but most of that we've already gone over. There's only a couple more tricks for re-expressing things. One thing you have to do is now, like I said, this table now is finished. We've finished this table and now it has to be memorized. I think you might already be pretty close to having it memorized, but anyway, make sure that you have this table memorized for tomorrow. Here's the new entries that are a little bit tricky. This one. Here's the inverse trig functions. Those are a little bit tricky. When we talked about this before, I think you had those down, but you want to make sure that those are really ultra memorized for tomorrow because you have to be comfortable with those ideas in order to do multi-step problems. So one thing you can do to benefit us for tomorrow is make sure you have those ideas down. And then we just did a whole bunch of little problems today about the types of antiderivatives you have to find. So hopefully having those in your notes, and hopefully you'll just go back and redo them until those are easy for you as well.